Okay, welcome to the SNARS monthly meeting. This is the presentation section for November 6th, 2021. This is Barry K6ST, your Zoom host today and one of the board members. We have a special guest, Rudi Wiedemann, Kilo 7 Romeo Alpha Whiskey. I guess the letters are for his call sign. And he's going to be giving a presentation day on NanoVna and applications for antennas and antenna tuners and things like that. Before we get started, just a couple of things. He has two cameras. I'm going to be going back and forth. One you can see right now is pointed on his screwdriver antenna, and on the screen. Oh nope, I have to. Well, it's not yet. Rudi, say something for a sec so we can say it because
Hello. Test 1, 2, 3. Do you copy, Barry?
That's why it says on mine it's that way. But there's when he's on, he'll either be his camera in his shack or another camera, which we'll put on in a minute, which will go to his NanoVna. So we're going to be going back and forth. We're going to go for a little over a half hour, 40 minutes max today. If there's questions along the way, if they're in context, go ahead and type them in the chat. Rudi will look at them, and if they're applicable, he'll answer them as we go. If we have time, we may take a few questions along the way. We'll take a few questions at the end, and then for sure in the next segment after we stop the video, which is the open Q&A for anything, which is anything about the club or ham radio or even more in the presentation, we have time there. So without further ado, let's go to Rudi, K7 RAW. Do an introduction, and then we'll do the first poll. Go ahead, Rudi.
All right, Barry, can you hear me?
Yes, perfect.
Excellent. All right. Well, good morning, everyone. We have a big turnout. Thank you for coming. That's pretty exciting for me. I want to first thank Barry for all the effort of setting this up. We talked about this several months ago. I think it was the August Zoom meeting. You suggested this. And I put in a fair bit of time to prepare, and Barry and I spent 2 hours yesterday just going through the technical stuff to make sure this came off all right. So thank you, Barry. Kudos to you. So without further ado, what I'm going to do is have a couple slides to kind of lay the groundwork of what we're going to cover, and then we'll jump right into it. So Barry, I'm going to...
Quick question. Do you want to do, and it's up to you, do you want to do the slides and then the opening poll? Or do you want to do the opening poll and then the slides? What's your pleasure?
Why don't we do the slides first, then we'll do the opening poll while you and I switch over to the camera.
Sounds perfect.
All
Go
right.
ahead. You should be able to do a screen
So
share.
let me share my screen and put it in full screen mode. All right. Can everybody see that's the slides?
You're good on this end.
Okay, so today we're going to talk about the NanoVna. We're going to talk a little bit about some of the applications, but mostly about the unit itself and what it can do. And think about this NanoVna as being kind of like a window on an entire universe of radio antennas of all types. And we're going to just basically peek into and through this window. We're not going to step through the window today. That's a lot more to discuss, but we're just going to take a good tour with some applications. Okay, so first we're going to do an unboxing of my VNA, show you what comes in the kit. We're going to do an overview of the capabilities. We'll do a review of the different versions. We'll set up the initial format, give you a tour through this unit, do an actual calibration, give you some tips and tricks, and then we'll do a live demo of tuning a short vertical screwdriver antenna, and then we'll do a wrap-up Q&A. Okay, so there's a lot of flavors to the NanoVna. On the upper left, you see one of the early versions, which is a open frame sandwich PCB type version with SMA connectors. Below that and to the right, you see one of the earlier versions. You'll recognize it because it's got a thumb wheel in the upper right. That wasn't all that reliable. So if you have one of those, don't be too surprised if it craps out on you on that thumb wheel. To the upper right of that, with the big fat connectors, is the SAA type with N connectors. They're bigger than SO239s. And then on the lower right is the NanoVna-F version 2, and that's the one I have, and that's one you'll be looking at today. Little quick comparison. While there's many others, including some El Cheapo clones, they run around $60 to $120 typically. I'm showing you 4 versions that I just showed you the pictures of. The one on the right is what we'll look at today. My version, I like it because it has the bigger screen, has much higher resolution. It has more data points that it can store, much bigger battery. SMA connectors, I've never had a problem with SMAs, and it's got a full aluminum full box frame, which is nice. I've actually dropped it on concrete. It scratched it, but it didn't phase it whatsoever. So I can attest that it's a pretty rugged little unit. So a couple accessories that are also useful. On the left, you see a little demo board with a variety of little circuits on there and UF.L connectors on there that come with it, little cables that come with it, all kinds of little circuits that you can actually use to see the effect and the results on your NanoVna. In the middle, you see a little test board. That's an inline test board. I have both sitting here, so if you want to actually see what they look like in my hand, I can show them to you. And to the right, of course, adapters. We all love adapters. Never have enough adapters, and so that's always good to have is some useful adapters. Okay, so what can this bugger do? Obviously, the first thing you want to do is some SWR sweeps, right? It can do antenna impedance and frequency analysis on a Smith chart, which we'll show you here, and we'll show you how that works and why that's extremely powerful. You can get phase angle between voltage and current. You can get return loss in dB down from 0. You can measure actual inductor and capacitor values, a lot of which we're not going to go in today. That's more advanced, but just want to give you a flavor. It can read out the L network solutions to achieve resonance, which is really cool. It actually solves the equation of your match circuit. You can do inline network analysis like filters, and you can do field line analysis. It has the ability to do time domain reflectometry. Now, I will say that's what my unit does with the latest firmware update that just came out 2 weeks ago. I won't say that all NanoVNAs can do all these things, but most can do most. The later versions will generally do all, but most of them are all firmware updatable. When you look for one, I would recommend you make sure that it's well supported by a good flow of recent firmware updates, because that makes a huge, huge difference on the versatility and usability of this thing. Just a recap. You'll see inductance in henries, capacitance in farads, and then of course in a scale you got milli, micro, nano, pico, and femto. Micro, of course, is 1 million, nano is 1 billion. Capacitance is usually in picofarad, and inductance is usually in microfarads. All right. Radio is a system. You need to think of the antennas as a system, starting with the radio, maybe with an tuner inside. Feed line could be coax, could be ladder line, could be something else. You might have a current choke and a balun in line, hopefully. We'll talk a little bit about that later. A solid electrical connection to the antenna, and the antenna wire itself, whether that be a dipole, vertical, long wire, whatever. So you have to think of the antenna as a system. And when you use the VNA, it's important to calibrate that at the appropriate point, which we'll find out here in a minute. So that's my presentation, Barry. So if you want to go ahead and start the initial poll, we're going to do a preliminary poll. Then we'll do a little quick poll at the end to kind of do capture some of your impressions. So I am going to turn it back to you. I'm going to, I guess, stop sharing my screen.
Yeah, I stopped sharing it for you. Okay, thank you very much for the introduction. So there's a beginning poll. There's 4 questions. Yeah, I'm going to just read them out loud, so it's on the on the recording. But if you kindly fill it out, and let's see here. I got to go to somebody who's not a co-host. So it doesn't look like anybody's filling them out yet. So I might need to relaunch it. Hold on, we got a little technical issue here. Wes, can you unmute
I'm filling
yourself?
it out.
Okay, you are. Okay, good. Thank you. Okay, no worries. Okay, so let's just take a moment to do that. Okay, so while you're filling it out, just for the recording, there's 4 questions. First question is, are you familiar with the Nano VNA? And the answers are yes, I have one. Second choice is I have used one before. That probably means you don't have one, but you've used one or you've seen one. And the third is I know nothing about them. Okay, second question that people are filling out is, where do you operate your antenna? It's a multiple choice. So there's lots of things. I do it at home in an unrestricted space, maybe an apartment, a condo in a restricted space, mobile, camping or RV, POTA, parks on the air, and summits on the air. And somebody said it won't take a submit won't work. Try it again. It must be a system glitch. Keep going. Or summits on the air. Third question is, how restricted space do you have? And it's a bunch of answers all the way from I have unlimited space to I have limited, above ground, balcony, indoor, attic, rooftop, other. And the last question is, what sort of problems might you be having with antennas? High SWR, low efficiency, poor signal reports, weird SWR. I get that sometimes. RF in the shack, other. Okay, let's give it another 30 seconds or so. We have people are still. We have about 70% have done that. Okay, some people say they can submit, some they can't. There might be a little glitchy today. Okay, we're just about to close the poll. Anything you want to say right before we close it and show the results, Rudy?
No, I think this is a great idea, Barry. It gives me an idea of what people are interested in. That way I can tune my presentation.
Okay, so hopefully people can do it. Not everybody can submit. Sorry, sometimes there's glitchy stuff in Zoom, not usually, but anyway. Okay, so I'm gonna stop the poll and I'm going to share the results. So you should be able to see it on the screen, including, do you see the results also on the screen that I have there, Rudy, or not?
Yep, I see them.
So you want to read them out or just share anything about it before we go on? Because I think they're interesting for the recording also.
No, I think let's move on.
Sounds good. So I'm going to stop that. I'll just say let me just read the top answer out of each. I think that might be interesting real quick. The Nano VNA, the highest percentage of people is people that don't have one. So a lot of people are new. On the antenna, highest is home unrestricted. The highest for your space is unrestricted. So a lot of people have that, although some are restricted. And lastly, the largest is low efficiency and other issues. Okay, take her away. Tell me where you want to go. Do you want to go on to your Nano VNA for the video?
Yeah, let's do that.
Let me go to that other screen, and we'll get you over there. Okay, so your Nano VNA should be up right now, or at least that screen. Go ahead.
All right. Can you see the Nano VNA?
Well, I see what looks like a white strip. I wonder what it is.
All right.
There's fingers there.
All right, good. So we got the right camera. We're doing 3-ring circus here this morning. All right, so let's take a look at what you typically get in the goodie box. So this is a menu. That's the menu map of all the functions in the Nano VNA. You usually get that, but you can also download that. So let's set that aside. And let's see what we get here. What we got is the Nano VNA, and you got a couple very important things over here. These are your calibrators, which you'll use in a second. These are, they give you a couple of jumper pigtails. which we'll show you how to use. And these are a couple adapters, which are very useful when you use it with the pigtails. So let's go ahead and set that aside. Let's take a look at the NanoVna itself. Again, as I said, this is the F version 2, the high-res version. I like resolution, and I like big screens. So that's what it looks like when it first comes up. And one of the things you get with this is a stylus, which we'll use. Now, let me give you a quick tour. What you're looking at is you're looking at two traces, the yellow trace and a green trace. And the ordinate is marked on both sides the same for what is highlighted, in this case, the SWR trace. And we're showing SWRs from 1 to 11 on this right side, which we can change pretty much everything here. And we're also seeing a Smith chart. So one of the first things we're going to do is get the settings set up so that we can calibrate this in the right range, for the demonstration today. So what we're going to do is, and I always recommend that you do this first. First, let's set the frequency range. So you touch the screen anywhere and you say stimulus. Stimulus start. We're going to start at 10 megahertz and we're going to stop at 30 megahertz for today. All right. Now down here, you'll see two very important things. You'll see OSL and then C star. Okay, that means it's been calibrated already, and I've got 201 points. 201. Why 201? Because you got 1 point on either side and 199 data points in between. So that's 201. How do you do that? What you do is you go back here and you say, I think it's configuration. Oh, let's turn the brightness down on this. This might help. Barry, can you see that better? Is the screen showing up better now?
A little better, and just for everybody to know, because of between the camera onto the backlit VNA, some of these details we might not be able to see, but Rudy's going to try to explain them as we go.
Right. So I will talk you through what I'm seeing on the menu here. So in the config menu, one of the things is sweep points. So I say 201, okay. And now you see 201. So now I've got my frequency band and I've got my number of sweep points. That's important to set very first thing before you calibrate it, because you're going to calibrate according to the frequency band, and you're going to put as many data points in that frequency band as possible for the calibration and for your measurements. So that's an important thing to set up. So let's talk about calibration. What you're seeing is a Smith chart, and when you calibrate, there are three critical points. The very middle of this circle in the Smith chart relates to 50 ohm resistance. That's the radiation resistance of the antenna. And we calibrate that to 50 ohms with a load as part of the process. The very left end at the tangent here and along this horizontal axis, right through slicing through the middle of the Smith chart, is a short or 0 ohms. And over here at the very right end is open or infinite ohms. So it's a logarithmic scale from a short to an open with 50 ohms in the center. These curves that come up are reactance curves. The ones that are above the line are inductive reactance with a positive J value. Anything below this line is a negative reactance with a negative J value. And you see the Smith readout is resistance of 133 ohms right now and a J value of 29. So it's slightly inductive. And we'll get into talking about that a little bit more here in a minute. So let's go ahead and calibrate. So what we do is we go back and we say cal and we say calibrate. And let me get out our little calibration goodies. All right. So the first thing we want to see is we've got these little caps, and this one is empty inside. Okay, so that's the open. So I'm going to put that on here. Just spin it there. Press the open button. Wait a few seconds, and it goes beep. take this guy off. This one has a pin inside. I don't know if you can see it, but it's got a pin. That's the short.
Yep, we can see it fine.
And this guy, we spin that on here. Just make it snug. You don't have to take it terribly tight. And that's done. The third step is a load. That's this guy. It's a little bit bigger. And that's the load. Make it snug. Okay. And then the last step, just for completeness, that not that you have to, by the way, but for completeness, I'm going to show you the calibration, the through calibration. Now, I should mention what are these two ports, all right? This is the port where it sends a signal out and looks for the reflection back, okay, on port number 1. This port is an input port. And so this is the signal generator port, generates a signal out. And then what we're going to do is we're going to actually do the calibration looking for the signal coming in. So you take one of these little cables that comes with it, and you simply hook it up to the out port number 1. You hook this up to port number 2. Nice and snug. And then you say through. All right, now you say done. And we're going to save this in slot number 1. Okay, so now let me go back and show you something useful. I'm going to put the 50 ohm load back in here. And you should see on the Smith chart, our little green marker, which is our Smith chart trace. Our green marker is right dead nuts in the center of the Smith chart circle. So it's calibrated nicely to 50 ohms. So we have a good calibration, and we saved it to slot number 2, I believe. Okay, so now that we're calibrated, let's do one thing. Let's turn off for clarity's sake. Let's turn off the Smith chart trace. So I go to my display, I say trace, and I touch on the green trace until it disappears. Now I can go back, or I can just touch anywhere on the screen. So now I have an open here, and I see infinite SWR, as you can imagine, with an open. All right, so now, Barry, if you want to switch over to the other camera to show you what we've got for an antenna, what we're going to analyze today. I'm waving my hand now.
Yep.
And
We have your antenna.
So what I've got here, folks, is a screwdriver antenna, a DC 12-volt driven screwdriver with a telescopic whip about 7 feet long, and a couple of radials underneath that as a stinger. I've also got a current choke hooked up to the bottom, feeding the bottom base of this screwdriver, so that I can isolate my coax from my antenna. So I touch ground, nothing will happen to no goofy things will happen to the SWR, which is useful. And I got a little up-down driver to it. So what I'm going to do now is I'm going to hook up pardon me, I got a table full of junk here. I got to find the connector. So I'm going to hook up the antenna, little 6-foot coax. And we see.
Okay, hold on, Rudy. Let me flip it over to the to your other camera so we can see the VNA. So now we're on the VNA camera. Go ahead.
Right. Okay. So you see some garbage up here, but this is the main trace. So, and remember, we're now going from 10 to 30 megahertz. And so what I'm going to do now, which is a really cool function, is I'm going to actually track the minimum SWR. And so I'm going to go back here and say marker, search for a minimum, and turn on tracking. And I'm going to go back, and you'll see a little marker number 1 down here, right there at the bottom of this trough, right here. And you can see that here it is 10, 15, 20, 25, 30 megahertz. So we're sitting just about 17 megahertz is where it's resonant right now. Okay, this noise is probably,
yeah, read that number up above that because it's a little hard to see on the screen.
okay, so this is 1.24. So I got about a 1.2, 1.3 SWR at the bottom of this. So it's not bad. And it's telling me actually where that is. It's 16.5, 16.6 megahertz. And this is the reason why you want to set your frequency band first and maximize the number of points, because it puts all those points, spreads them out to get the best resolution of these curves. If you left the default of 50 kilohertz to 3 gigahertz, and then you zoomed in from 10 to 30, you'd only have a few data points and you wouldn't have a very good graph. So it's important to use your data points wisely. Okay, so what we're going to do now is we're going to have some fun. We're going to try to tune this antenna by moving the screwdriver antenna so that we can get it into the 20-meter band, right around 14.2 or 0.25, somewhere right in the bottom of the phone band. So if you, what I'm doing is, for those of you not familiar with a screwdriver antenna, it basically adds or subtracts inductance at the base of the antenna so that we compensate for an otherwise normal capacitive antenna because it's shorter than resonant, normal, natural resonance. So
we're on the camera right now of the screwdriver. So is it going up and down? Yeah, you can see everybody. You can see the screwdriver. The coil in the screwdriver is going up.
Okay, so now look at where the bottom is right now. It's telling me it's
let me get back to your other screen. One sec, Rudy. Okay, so we're going to go back to the VNA. Now we have the VNA back up. Go ahead.
Yeah, so we lucked out. We're sitting right around 14.2 megahertz. And so I'm just going to tool around and show you that we can actually, how the screwdriver actually does its thing is actually pretty cool. So I'm going to continue going down in frequency. And again, you got to wait until it settles out. Give it a second, and there. And now you see it settled out down here at 13 megahertz. I guess it's around 13.0 megahertz. So you can see how tuning this antenna live and whether I'm adding or subtracting coils, or I'm adding or subtracting length on the antenna by trimming it or soldering on some extra, is all a matter of how you get this to resonance. Now, let's talk about resonance and let's talk about resistance and SWR. Something very, very important. And okay, so I'm way up there. I'm actually probably off the right end of the screen right now. So let me bring it back down and let's get it back on the screen. All right, so there we're back on our screen. And let me see where we are now. And we're at around 18 megahertz. Let's go back into the 20-meter band, and then we're going to zoom in, and I want to show you a couple of interesting things. So let's get back down here. Where are we? 14.4. Let's let it settle out a little bit. 14.5. Let's bring it down. And I'm tapping it a little bit, and I'm just, there we go, scooching it down. 14.2, 14.3. Perfect. Okay. So we're right down in 20-meter land. Okay, so now what we're going to do is, since we're interested in 20 meters, we're going to change the stimulus range from 13.5 to 15 megahertz. So stimulus start 13.5 megahertz, and stimulus stop, we'll make that, well, let's just call it 15 megahertz for grins. Now you can look at the curve and you can see my SWR. Now you can see that a lot of it's below 3. So I don't need all this extra space up here. So what I'm going to do is I'm going to change the vertical scale on the SWR. All right. And let's hold on a second. Let me go back and let me change the display scale. All right. And we're going to say 0.2. and that's 0.2 of the normal full scale 10. So right now, and it rounds it up. So it's beautiful. It's 1 to 3 SWR, which is really, really nice. Okay. And let's just see where our marker is. Okay. Let's do a search. Tracking should be on. Yep, and tracking is on. You see our little marker number 1. You have up to 4 markers available that you can dial in, and the readout of the marker comes out right here. We're at 14.272 megahertz with an SWR minimum of 1.04, which is not bad. I'll take that any day. Some of this noise is coming in either due to capacitance or other stray effects here, but we're zoomed in quite a ways, as you can tell. We've only got 1.5 megahertz across the entire band here. Now I'm going to show you something really interesting. I'm going to turn on the trace for the Smith chart. I want to explain something, what's going on here. This green trace, this arc, is the Smith chart. And once I engage the Smith chart, it stops my auto tracking of my trace, because right now I'm on the Smith chart. You can see this is a highlighted block. Let me go back to SWR and highlighting that. And now I got my SWR graph over here, or I can touch on this, okay? I can also touch on a variety of different things here and change, it'll automatically pick up on that. So touching on things actually lets you adjust it depending on what mode you're in. But the thing I want to point out right now is the fact that looking at the Smith chart, there are 3 buttons over here. There's a marker up, marker down, and the center button brings up the menu. So I'll just touch the center button for a second and show you that it brings up the menu. Okay, touch it again, it clears the menu. So what I'm going to do is, my marker is right now at the top of the curve. I'm going to press the down marker button. And now what I want to show you is when I get that yellow marker down here at the bottom, right here, look at where, whoops, where did I go? I touched something and I moved the marker again. Let me do one thing. Let me make sure that my marker is tracking is off, just so that it doesn't want to move it around on me. So let's get it back down to the bottom of the curve. And all right, now it's stable and it's sitting there. Now I want to show you something interesting. Look at the little marker number 1 here that's in green on the Smith chart. I don't know if you can see it, but it's right here. It's almost exactly in the middle of the Smith chart, very close to 50 ohms. In fact, it's 41.5 ohms, 43.1 ohms, bouncing around a little bit. So it's around mid-40s, low to mid-40s in ohmage. And your SWR, and this is your radiation resistance. So this is your impedance, your real value, which is the resistance, and your imaginary value, which is the reactance. And the resistance part, if you divide that by 50 or 50 into that, that gives you your SWR above or below 50. We're below 50 ohms. So that's where if you divide 50 by 47, 45, you get a 1.05, 1.1 SWR. If it were above 50, by the same ratio, you'd also get the same SWR. So it's whether you're above or below 50, that ratio, either way, it gives you your SWR. Now, an important concept is that not to be confused with the reactance, and it's the reactance that controls your resonance. Your SWR controls the impedance match between your transmitter and your feed line system and your antenna. So right now it's really close. It's -2 ohms. And again, reactance is also in ohms, but it's a J value. And tells me it's very, very negative, it's very slightly capacitive. So it might need a touch more, but we're not going to mess with it. We're so low. J values will often go into the hundreds or even thousands sometimes. So a J value of 1 is nothing. So I wanted to show you that you can actually see this arc is the impedance, the complex impedance as a function of the frequency. And of course, the SWR, you see that sweep scan as a function of frequency that's displayed differently. So I want to show you one other important thing about the Smith chart is I can actually display it. I'm highlighted on the Smith chart, so I'm going to display, let's see, format. I'm going to change the format from R plus JX, or complex impedance, to R plus LNC. And now I've got the resistance, but I've now got the reactance now in terms of capacitance or inductance. And it's so close to zero, it's bouncing back and forth between nanofarads and microhenries. But you can see now that this is either a capacitance or inductance. So that is the natural capacitance or inductance of the antenna. Now, one of the things I didn't do, I neglected to do, is I calibrated this unit right here at the input port. What I really should have done is calibrated it at the where it came into the antenna. And so what I should have used is I should have used one of these little SO239 to SMA connectors and plug this into the end of my feed line coming from my NanoVna. So I can take into account anything I've got and have this right there where the antenna wire itself would connect. And that's when I would do all of my calibrations at that point. So that's called the calibration plane. And always remember to try to do your calibrations at the antenna plane of your system, wherever in the system, wiring system you have, wherever that falls. So it's a lot of information we've already covered. And it's 9 o'clock, so we're doing pretty good on time. Are there any questions so far?
One question, I'm going to open up the mic here in a second. Oh, actually, if people have a question, verbal question, just raise your hand. It's on the reactions, and you can reactions tab. One question they have is, where do you buy them? There's a little chat back and forth. You want to mention about that?
Well, I bought mine on eBay, and like I said, I paid, I think, 125, 130 bucks for it. It's the high end. This is the high end model, but I like the resolution of the screen. I should also mention that they all have a USB port that goes to 2 different software packages. And I forgot the names of them right now, but you can download the software on your PC or Mac and actually see this in much higher resolution with a whole bunch of other markers and all kinds of analysis tools on your PC. But what I wanted to focus on today is this unit itself, because this is what you're likely to be carrying in the field. Maybe you won't carry your PC, but this is easy. You can put this in your shirt pocket. So that's what I really want to focus on.
I have a question, and that is this rechargeable? How does the
battery? What's really cool is this particular one has the biggest battery in it. It's got a 5,000 milliamp hour battery, and I've run this all day, and I've not run out of juice. And it's a USB-C, USB-C port, charging port on the side. Let's just show you what the side of this looks like. Let me unscrew this here. Maybe I should have actually shown this to you first. But so you've got a USB-C, you got the on-off switch, you've got an output, which will actually output 5 volts at 1 amp as a power source if you want to use the battery as a power source. And here's your center button and your up-down marker control. And of course, on the other end, you've got your transmit and your receive, nicely marked. And on the back, a little bit about how the ports, what they do and how they're configured, what to use them for. By the way, when you've calibrated this, one of the things you'll notice is you'll see OSLT and then a C star. That means open, short, load, and through have been calibrated. And C star means that has been assigned to a storage. And the storage that you, let's go back and take a look at Save Recall. if you hit recall, it'll actually show you the frequency band that you calibrated in, and which is pretty nice. You've got 7 slots, and I use the 7 slots. I actually marked them slot 1 for 10 meters, 2 for 20 meters, 3 30, 4 40, 5, I think for 15. There's a 5 in there, so 5 for 15, and 6 for 80 meters. So those are the bands that I usually allocate that to. And when you do a recall, it recalls the all of the scales, the frequencies, the vertical scale, and of course the corresponding calibration that you stored in that slot.
Great.
So
Also, a few more questions when you have a moment.
sure, go ahead.
Okay, so there's 3 or 4 more on there. Okay, so one of the questions is, can the original article, let me just read it and we can dissect it, be easily distinguished from the Asian clones? I think he's saying, is there a difference between a clone version of buying one of these, and the real deal? Is there like a main manufacturer?
What I've seen is, well, I would recommend that you do your homework. There's several websites up there that will actually tell you which ones are clones and not, and how to identify them. I know the one that has a picture of a gecko on it is a real cheap knockoff that they don't recommend, and there's not a lot of support for it, but it's like super cheap. It's like $40. The base price I've seen is around $60, and the high end is around $120, $130 for a unit like this one. But I would just recommend you just do a Google search on NanoVna comparison or versions, and or clones, knockoffs, and there's just tons of information up there.
Okay, a couple other questions. Great info. Can I download the video to refresh the memory? Is the question.
Okay, so if you're talking about capturing the actual trace that we're using, yeah, let me show you it's called a storage function in the menu. So let's just say we want to capture the trace on here. Let's do it. So you go here to storage, okay, and you'll see that you can store either what's called an S1P or an S2P file. These are our touchstone files. The S1P is what is the output and signal reflected of port 1. S2P is what's coming into port 2 if you had some kind of a through filter or something like that. So it generates files. Those are ordinary text files, comma separated, CSV, so you can import it into like Excel as a CSV. And it gives you a list of the frequency, comma, and then the real part of the impedance, and then comma, the J value or reactance component of the impedance at that frequency. And it gives you a list of that for 201 if you've got 201 data points. So if I say S1P, it stores that and just tells me that it's in there as an S1P. And to get it out, I plug in my USB into my PC and I boot up holding the middle button here on the right. You hold that as you fire up the unit after it's plugged into the PC, and it creates a virtual U drive on your PC, opens that up, file manager, and you'll see the S1P file in there. And what's really cool about that is you can literally import that directly and load that and fire up SimSmith right in with the S1P, and it'll actually load in that entire scan into SimSmith, and now you can play around with all kinds of matching circuitry and all kinds of stuff with it to see how you want to compensate and correct and modify the signal response of the system.
Great. By the way, for everybody else on the chat, which you guys go to, Derek mentioned there's free PC software, so there's software there. Okay, a couple more questions. One of them is, please explain more about what you mean about the antenna connection plane for calibration.
Okay, good question. So here's what I'm going to do, is I'm going to unscrew the, what I've got is a little box that has a current.
Get a little closer to your microphone. We lost your audio.
Yeah, can you hear me now?
Yeah, but it sounds like you're way away.
All right, stand by. I'm unscrewing the coax and current choke box from the base of the antenna. All right. So
we see a difference in the Nano VNA.
Right. So hang on a second. Let me unplug it from the antenna so I can get untethered here. All right. So what I've got is a box with the input coax cable from my Nano VNA coming in from the Nano VNA to here. But this is what's actually plugged into the antenna. What's inside here is a current choke, which is basically you take like an FT240-43 or -31 material, and you wind yourself a choke. We can talk about that at a seminar sometime. But this is where the antenna actually plugs in. So where I really want to calibrate is right here. Okay. So,
and the device that you're holding in your left hand is what? What is that black box?
Okay, what I built in the black box is a current choke again. And what a current choke does, let's take a few moments to talk about this, because this is really, really important. A lot of people are confused by balans and chokes. Okay. And I'm going to tell you guys a big secret of how you can immediately improve your whole antenna system and rig. Maybe even if you've got all the stuff, you could do it today. All right. And that is, number one, if you've got your coax coming in from your radio here, and it's connected directly to the antenna, which it very often is, then what can happen is, like a dipole, for example, you'll actually have the outside of the braid of your coax becomes part of your antenna system if you did that. Okay. Well, that's no good, because if you move your coax around, blows around in the wind, somebody walks near it and you've got body capacitance, it'll throw your SW all to hell. And so what I recommend is you build or buy, you can build these very easily, is what's called a current choke. Here's a little baby brother that I wound. This is a current choke. And it is basically a transformer laying on its side. Okay, this bifilar, black and white wires wound, about 12 windings around this, and you put the input from your coax here, and you put the output here. And what this does is it isolates your coax. RF isolates the coax line from your antenna, and now your coax is no longer part of your antenna system. It just feeds the power to your antenna, and you'll see a huge difference that way. Barry can attest to the fact that he borrowed one of my current chokes, and then even though he had it backwards, it already helped him out. So that's a current choke. That's the first thing you want to do, is isolate your coax. But the second step you want to do is then use a Balan if your antenna's natural radiation resistance is way off from 50 ohms. So for example, a NFED half wave will be typically, well, let's just call it 450 ohms for easy numbers sake, okay? Now, that's 450 ohms, but your coax, all right? Your coax is, of course, 50 ohms. So how do you get the matchup? Okay, otherwise your Smith chart's going to tell you 450 ohms, and that's no good. What I'm talking about is impedance matching, and this could be a long discussion, but it's basically, it's a lot like a 10-speed bicycle, right? If you're pedaling uphill in 10th gear, you ain't going to get very far. You're going to work real hard and not go very fast. If you're in first gear going downhill, you're going to be pedaling like hell, but it's not going to get you any faster. Depending on the load, or whether you're going uphill or downhill or on flatland, and how fast you want to go and how much power you want to put into the system, all right, will depend on which gear you want to use. Well, that's your impedance match. So with a 450 ohm natural resistance antenna, which you can analyze with your NanoVna, all right, you can actually see what the natural resistance is right here, and then say, oh, I need a 9-to-1 Balan. That'll get me right in the zone. So you put a 9-to-1 Balan, and Balan means balanced to unbalanced. So there's a third thing that's happening here. When you have a coax cable, take a look at an SO239, all right, the outside is the braid, and the inside is the conductor. Well, the braid acts like a shield, okay? And that's an asymmetric system compared to something like a dipole antenna or open ladder line, where one is not shielding the other. When you've got something shielding, that's an asymmetric or unbalanced system. Now, if you've got a dipole there, you've got a balanced system. Neither of those wires are shielding the other, so that's balanced. So now we need to go from an unbalanced to a balanced thing like a dipole, and that's what a bal-un does. Goes from balanced, your dipole, to your unbalanced, which is your coax. Now, if you're feeding it with ladder line to a end-fed half wave, okay, that end-fed half wave is an asymmetric antenna. It's unbalanced. And if you've got a coax, that's unbalanced, but you need a 9-to-1 ratio because that end-fed half wave is still 450 ohms and your coax is 50 ohms. So you need a 9-to-1 unbalanced to unbalanced antenna. So hopefully I've confused you enough that there's three things. There's the current choke that isolates your feed line. There is the Balun or un, which adjusts between your balanced and your unbalanced lines. And then finally, the ratio, which is your impedance match ratio. And then finally, the last thing is, of course, the reactance, okay? And that's this J value up here that you see. And that J value is controlling the resonance of your antenna, okay? Whether it's capacitive or inductive, or whether they're balanced, and that means that your antenna is now resonant, your antenna system. And that's what a tuner or impedance matching box really does, is it matches your impedance to get not only get your radiation resistance dialed in, but also your reactance dialed in. Your reactance close to zero and your impedance close to your feed line, in this case, 50 ohm coax. And then you've got the maximum power throughput from your transmitter out to the power being broadcast on the air.
Great. That's so great.
More questions?
Kind of one or two questions, and then we're going to end this portion, and then we can go into more detail.
Cool.
So one of them sort of a comment, and I'm going to do it with you. And the original question was, would you demo the TDR function? We don't have time right now, but I'd like you just in like maybe 30 seconds just to describe what the TDR function does.
Okay.
And I know in future things we can do that.
Okay, so there's a function here on the main menu called TDR. TDR stands for time domain reflectometry. And all this is this port number 1 sends pulses of signal out onto your coax and then listens for the time it takes for it to reflect back and uses that to calculate the length of the coax. Now, if I've got a 100-foot coax and it's coming back faster than I expected, then I've probably got a short from a kink in the middle of that coax, and it'll actually tell me a pretty good idea where that kink is, either an open or a short in the coax, something other than what I would expect. So that's a very brief explanation of TDR, but we're not going to demonstrate that here today.
Do that in a future seminar. We're gonna pull that in just a minute. Two other quick questions.
Yeah, go ahead.
And then we're going to end this section. Somebody says they've got an antenna. They happen to say it's a ham-stick dipole, but it's antenna. How would they determine what Balun they need to match the impedance with the coax? Okay.
Well, this guy will tell you straight away. By looking at the readout of the Smith tag here, it tells you.
But it says a little small to see.
Right. It'll actually tell you the resistance value here. So it's that R value out of the R plus J value, okay, of your impedance. The R component, the real component, which is your radiation resistance for the most part, if it's close to 50, you're good to go. If it's way off from 50, you need a balance. So for example, let's just say your antenna is sitting there right around 200 ohms. So you'll see this number to be right around 200, okay? Then you'll go, oh, I've got a 50 ohm coax. I got an antenna impedance of 200 ohms. I need a 4-to-1 Balun. There you go. That's how you calculate it. Now, there's nothing magic about 4-to-1 versus 5-to-1, 6-to-1. All it means is that the transformer, remember, impedance is like resistance, but with a frequency component to it. And so resistance is simply voltage over current, right? So it's the ratio of voltage to current. Well, remember that in a transformer, if the secondary has 2 times the winding of the primary, then it doubles the voltage. But because I have to have a conservation of energy here, law from physics, it has to chop the current in half to have the same wattage coming through that transformer, assuming a perfect transformer. So my current goes down by 2, my voltage goes up by 2, therefore the ratio or the impedance goes up by 4. And that's why a 4-to-1 Balun will have a secondary with twice the number of windings. If it's got 3 times the number of windings, guess what? I got a 9-to-1 Balun. That's how Balun ratios work. But I could wind a Balun with something other than an integer number. I could wind it with a ratio of 1.5, 2.5, 2.7, whatever, depending on however I want to wind my Balun ratio. So here's a multi-winding Balun that I built. This is 4 wires, quad filar wound together, 4 of them together as a group. And this will actually allow me to go and switch between 4 different ratios from 1 to 2, since I'm switching down because I got a short antenna, from 50 to 25 to 12 to about 6.5 ohms. Which is really nice because that's the range in which my short antennas tend to be for the different bands. So I could literally put a rotary switch on here and switch across and build a little box that lets me get right in the kill zone, and the rest can be taken care of by my internal auto tuner in my radio.
Just from an practical application, am I correct by saying when you start putting inductance or capacitance in there, or the balance in there, you'll see the result on the NanoVna of what it's doing.
Right, and you can actually try that with one of these little test boards. Here's an in and an out, and you can plug in different components, L and C components, wind your own coils like I do, put a couple of capacitors in here, whatever, build a little L network, pi network, T network, whatever, and actually see the performance immediately on your NanoVna. The last thing I want to point out is another cool thing, which is a demo board, okay? And that's this guy here. And that actually has a bunch of little circuits, little micro UF.L connectors on it, and some little micro UFL connectors that come with it on little cables to SMA. And actually you can see what kind of Smith chart and what kind of graph functions you can see on your NanoVna when you've plugged in these different circuits. You've got a notch filter, you've got different frequency responses here that you can see, and then you've got another short, open, and load calibration for this board alone. So that's a very useful thing to be able to play with and learn more about the NanoVna. It's a good tool.
We're going to have one closing question, and then we're going to stop this section of the recording, and then we'll go for more in-depth Q&A for this and other questions. The final question is what the NanoVna F, and I guess you have a F- version 2. What frequency range does it come in? From what to what?
For frequency range of the NanoVna?
Yeah. Mm-hmm.
Yes. It depends on the version. A lot of them are only up to 900 megahertz or 1 gigahertz, somewhere in that range. This one happens to be to 3 gigahertz. Some of them I've seen as high as 4, but they'll have different connectors, like an N connector, which is kind of a weird connector for me. N connectors are great if you're working up in UHF and gigahertz and that kind of band, but I'm mostly working HF and UHF, VHF. So the SMA and SO239 type connectors are great. But most of them now will top out at 3 gigahertz, which will allow you to analyze Wi-Fi antennas, which is pretty handy.
Very cool. So we've been going just about an hour, a lot of great information. John N7ROJ said it's the best presentation he's seen on the NanoVna. We will be putting the recording next week up on the SNARS SNARS YouTube channel. I'm going to give you a moment to, well, let me just do this. Why don't you do a closing for a minute or so, and then I'm going to do the wrap-up poll, and then we'll stop the recording and we can go into more detail in the next section, okay?
And by the way, I'll hang out here on Zoom if Barry, as long as Barry is willing.
Yeah,
I'll hang out for any further questions you guys want to talk about, more specifics about your particular situation.
Thank you so much, Rudi. People said great presentation. Let me just launch the final poll. And the question is, how valuable was it? Another question is, what was most interesting about it? Another question is, would you like to learn more specific areas? And last two questions is, Rudi's willing to do some more in-depth seminars in the future. Would you like to be on a fundamentals, in-depth fundamentals, and what about a hands-on solving? So just go ahead and answer those. While you're doing that, we're talking about maybe in springtime, when the weather gets good, when we get through winter, maybe doing something in the field with an antenna shootout. But that's a little farther down the line. So let's let people fill that out really quickly. Anything you want to say in closing verbally while they fill that out?
No, but all I can tell you is that with the NanoVna, I've always been interested in antennas, but I've never really had a good tool. My last was a MFJ 259B, which didn't give you a graphical sweep, but I sold it and for twice the price of what I bought this for, and this thing's got 10 times the function or more. So this gives me a window, a fantastic tool and a window on actually seeing what I'm doing. If you know how to interpret it and you know how to drive it, it's an incredibly useful tool. Probably one of the most useful tools next to my radio and a battery and a basic piece of wire for an antenna. So all I can tell you is that if you're serious about ham radio and equipment and setting up antennas, really understanding what you're doing, you would get one of these beasts and really master it, learn. And I'm happy to help you out through SNARS. Contact me, and I'm happy to help you with any of your problems using the NanoVna.
Great. Okay, I'm going to show the results here of the polls. Pretty interesting. So most people found it either extremely or very interesting today. People like different things. The largest was the usage of the VNA, then practical applications and overview. It's kind of the answer of what do they want to learn more. It's sort of equal across the board, but the highest one that stands out is antenna analyzing and impedance matching. And quite a few people are really interested in doing the fundamentals, and a little smaller percentage are interested in doing hands-on. So that's really great. Well, just thank you so much. And I just wanted to say the way Rudi showed up was he showed up on one of our calls and Zoom calls. Maybe it was a Monday night ham radio night. I said that would be really cool. Would you be willing to do it? That's how we find speakers. So thank you, Rudi. Can you give an email address or a way to get hold of you if they have any questions? Because it will be on the video.
Oh, sure. It's my first name, Rudi, at my last name, WIEDEMANN .Charlie. Charlie stands for the Cocos Keeling Islands that sells their registration domain names. Couldn't get .com, so I got .Charlie. Anyway, so that's how to get a hold of me. Drop me an email. Contact me through Barry.
K6ST, Kilo 6 Sugar Tango at ARRL.net. Anything you want to say before we end the recording and start the next section for the in-depth Q&A on this and anything else about SNARS? Anything else?
Not that I can think of. I think we've covered quite a bit.
This completes the presentation section on the NanoVna for the SNARS monthly meeting on November 6th, 2021, and repeat the email slowly. Just if you want to get hold of them, you can just send me an email. It'll be simple: Kilo 6 Sierra Tango at arrl.net. That's K6S as in Sam T Tango at arrl.net, and I can forward it. Okay, I'm going to stop the recording. Thank you so much, Rudi.
All right. Thanks, Barry.